Now we've already seen one power producing cycle. It was the Carnot cycle. We saw it on a PV diagram and on a TS diagram. And what we're going to do is kind of move away from that. Rather than relying on the Carnot cycle as our model of all power producing cycles, we're going to discover some other cycles, not really based on the Carnot cycle, that are idealized versions of various engines. And so we're going to develop some different cycles that will model different types of engines. For example, the jet engine cycle will be for jet engines. The Brayton cycle will be for gas turbines. You may not be familiar with gas turbines. There are some tanks that use gas turbines. There are a lot of helicopters, especially stat flight helicopters and helicopters that need to go fast, use gas turbines. And larger helicopters almost exclusively use gas turbines because you can get a very high power to weight ratio out of them. Diesel engines, of course, will be modeled by the diesel cycle, and the Otto cycle is what will typically model spark ignition or gasoline engines. So these are the cycles that we're going to look at that will get us closer to the behavior of these various types of engines, because there are significant differences between these types of engines, and we want to recognize the major differences, not the minor difference between various diesel engines or various gasoline engines, but the major differences across all these engines and versus the Carnot cycle as well. So we're going to move from something that's very theoretical, the Carnot cycle, to something that's much more real world. So you might say, well, why did we bother with the Carnot cycle in the first place? What good was it? Why didn't we just develop these ideal cycles? Because they're closer to the operation of actual engines and learn something about those actual engines. Well, the reason is because the Carnot cycle is one of the easiest completely reversible cycles, and what it does for us is it's kind of like the granddaddy of it all, right? It's the thing that says, here's the best you can do no matter what, because nature says so. Okay, I don't care how good of a jet engine or how good of a diesel engine you make, you will never get a better thermal efficiency than the Carnot cycle, because it's a reversible engine, and that's the best we can ever hope to achieve. Of course, we can never achieve it, but that's kind of like where the bar is set, right? We simply can't go faster than that. So that's the value of the Carnot cycle, and of any reversible cycle really, is primarily what's the best we can ever do with any engine. And of course we know that it depends on the temperature of the source and the sink, and so that actually helps us with all these real engines, because these real engines have similar characteristics to the Carnot cycle in the sense that the higher you make the thermal source for these engines and the lower you make the thermal sink for these engines, typically the more efficiently these engines will operate. So the Carnot cycle is very insightful and very useful, albeit very theoretical. So what do these cycles look like? Let's dive in and learn what these cycles look like. Let's develop them. Now, to develop them, we have to describe some of the assumptions we have to make. We'll make some assumptions called the air standard assumptions. Now, in a real engine, what happens is air is injected into the engine, fuel is put in, the fuel's burned, and combustion products are sent out of the engine. What we're going to do, though, is pretend that instead of having air and fuel put into the combustion chamber or into the gas turbine or whatever it may be, and combustion products flowing out, we're just going to assume that air flows through the engine instead. Now that may seem like a really bad assumption, because the fuel does come in and the chemical composition of the combustion products is different than the chemical composition of the air plus the fuel, right? It burned. So why are we doing this? Well, there's a couple of reasons. If you think about the air and the fuel mixture, there's more air than there is fuel by quite a bit, right? 14 to 1 or so. In the case of a gasoline engine, there's 14 times more the mass of air than fuel. So the main thing coming out in the combustion products is really the nitrogen that came in. I mean, after all, air is the biggest thing, in terms of mass that comes in, and the air is 79% nitrogen, so the main thing coming out in the combustion products is hot nitrogen. So it's not that bad of an approximation to say that air just flows into a heating section and leaves us hot air, or into a process where heat is added and the air is warmed up. Because that's really the purpose of the fuel. The purpose of the fuel is to generate hot air that can then be a good working fluid with a high amount of thermal energy. So what we're going to do is assume that the working fluid is just pure air, and it continuously circulates in a closed loop and behaves as an ideal gas. That'll make it easier for us to deal with it. And that's not a bad assumption for air. Air does typically behave as an ideal gas, because most of the time we're far enough away from its critical point that it will behave ideally. Now, there's something interesting here about the closed loop part. If we jump down to the bottom point, where it says the exhaust processes are replaced by a heat rejection process. Well, what is the purpose of putting the hot nitrogen outside of the car, out of the tailpipe? I mean, after all, the next car that comes along is going to scoop some of that up, right? I mean, it must. It's right behind it. Now, obviously, some more atmospheric air is mixed in with it, but you still get some of the combustion products into your engine. In fact, there's jokes like, that car is running so rich I can draft on him and run off of his exhaust fumes. It's so rich. But the point here is that instead of the atmosphere doing the cooling, we're going to include a process in all of our cycles where the hot nitrogen, essentially the hot air, is cooled down, representing the atmospheric process. So we're also going to assume that all the processes in the cycle are internally reversible. Now, this is different than a Carnot cycle. This is not a completely reversible process, but it'll make it easier for us to analyze these. And all we're really saying is that, for example, in a piston cylinder device, that the compression process has no friction and that it's reversible and that there's no heat transfer during it. And that's not such a bad assumption, because that would give us the minimum amount of, well, give us the maximum amount of work output from the power cycle, for example. The combustion process, as I said, is replaced by a heat addition process, since that's really the purpose of the fuel. Now, we can take these assumptions one step further with something called the cold air standard assumption. So all this plus the idea that the air has a constant heat capacity that we'll just take to be whatever the heat capacity of the air is at room temperature. So we'll look up Cp and Cv, and instead of allowing them to vary with temperature, we'll just take them to be whatever they are at room temperature and be done. Again, this is not perfect, but it's not bad, at least for the sake of simplifying and letting us learn something about engines. Before we can jump into engines, though, so many engines use reciprocating pistons that we need to talk about the reciprocating motion itself in some terms. Basically, what happens in an engine is that air is pulled in, the piston moves down, and of course the piston moves down. And you might think the piston sucks air in, but really the atmosphere pushes air into the cylinder. So eventually the piston reaches its lowest point, which is called bottom dead center. At that point, as in the figure on the left, the piston is at the bottom part of the stroke, and so the volume of the chamber above it is maximized. Well, that volume is called the volume at bottom dead center, BDC. The reason it's called bottom dead center is because the crankshaft has to rotate around to its lowest point, which is centered beneath the line of action for the rod on the piston, typically. Now, that's not always the case, but most engines, that's the way it works. So the volume at bottom dead center is really important, and it turns out that this piston, of course, is going to move back up in the cylinder for various purposes, various cycle or processes in the cycle. Sometimes it compresses the air, sometimes it's pushing waste gases out, but ultimately that piston will reach a maximum point where it doesn't go any farther. When it does that, there's actually still some space above the piston. It's not squeezed down to zero. If it did, it'd blow the head off the top of the engine, and that's not good, obviously. So there's always some what's called clearance volume, or the volume at top dead center. Top dead center is just the opposite point where the crankshaft has rotated around, such that the piston is at the highest point in the cylinder. So that's bottom dead center and top dead center. But there's another term you need to know, and that's the displacement volume. The displacement volume is the difference between the volume at bottom dead center and the volume at top dead center. And you can see it there shaded in pink on the left-hand side, where the total volume has been illustrated, but the clearance volume has been subtracted from it. So that displacement volume is something that we're particularly interested in. In fact, I just bought a car and it has a 2.0 liter engine. What that means is that 2 liters of volume, of air essentially, well, really volume, is displaced every thermodynamic cycle, which is 2 rotations of the crankshaft. If I got my facts right, maybe every single rotation. I don't think the engine's that big. No, it must be every 2 rotations for a complete thermodynamic cycle. So it's a 2.0 liter engine, and all that means is that not that the volume when the pistons are all down is 2 liters, but that the displacement volume, the amount of volume that's displaced, is 2 liters, or thereabout. It's probably rounded off a little bit. And of course there's some manufacturing imperfections as well, but nominally it's a 2 liter engine. Now we can draw a PV diagram for this process by taking the piston cylinder device and laying it on its side so that the cylinder and piston match the volume axis. And of course you can see the volume at bottom dead center where the piston is all the way to the right, and then the volume at top dead center with the piston to the left. Now the actual thermodynamic cycle is shown there, but there's a concept here that we need to talk about. called the mean effective pressure. But before we get into that, let's say one more thing about bottom dead center and top dead center volumes. You may have heard the term the compression ratio. All that really is the volume that's the maximum volume when the piston's all the way down at bottom dead center, divided by the minimum volume that the cylinder experiences when the piston is all the way at top dead center. So it's just Vmax over Vmin, and it's the volume at bottom dead center over the volume at top dead center. And this is what's called the compression ratio. It's just defined that way, and it's given the symbol R. Now, what about mean effective pressure? If you've ever been around race cars or compared engine details, you've probably heard the term mean effective pressure. Now remember, on a PV diagram, the area enclosed by the cycle represents the net amount of work done in one of the cycles. So you can see the Rio process up there that has, not sharp edges but smooth edges all the way around, and there's a net work enclosed in it. Well, that net work is a certain amount of work, right? How do we compare two engines? Let's say two engines have the exact same displacement, maybe a 300 cubic inch displacement. Okay, Chevy versus Ford. Okay, let's just go with that. How would you compare their ability of making horsepower per cubic inch? Well, you use something called mean effective pressure, and what you do is you say, okay, let's put bottom dead center and top dead center where they really are in the real cycle, and then let's figure out how much pressure we'd have to have so that the area enclosed by that rectangle you see there beneath the real cycle has the same amount of area as the area inside of the cycle. So whatever that mean effective pressure number is that's required so that the rectangle represents the actual area inside of the real cycle, that's called the mean effective pressure. So if you have two engines and one has a higher mean effective pressure, what that means is that for each cubic inch in that engine that's displaced, more power is produced or more work is done. Doesn't mean that that engine is a more efficient engine in terms of thermodynamic efficiency. It doesn't mean that you can get more miles per gallon out of that engine. It just means that this engine is more efficient in terms of its displacement being capable of doing more work. So it's a more efficient displacement, if you want to think about it that way. So by definition, then, the net work is equal to the mean effective pressure multiplied by the displacement volume, which is just the piston cross-sectional area multiplied by the stroke length of the piston. So we can take this and rearrange the equation to solve for mean effective pressure, and this is basically the definition of mean effective pressure. It's the net work produced by the actual cycle divided by the difference between the maximum and minimum volumes. Now we can also write this as the specific work, the work per unit mass of working fluid that goes through the engine, divided by the difference between the specific volumes at top dead center, well, bottom dead center first and then top dead center second. So you should highlight this equation in the summary at the back of Chapter 7. It is something we will use, and I'm trying to put boxes around all the really important equations as we go along. So of course compression ratio is something you need to know forwards, backwards, upside, downside, whatever. You need to be able to recognize that very easily. Mean effective pressure is important, but not quite as important as the compression ratio. So finally we can talk about the Otto cycle. Now I hope that this shows up well. I've got an animation on the right hand side, and at first it might look a little strange to you, but if you've ever seen a particular type of engine you might recognize it. In fact, what's happening is the working fluid is being shown. Now here some fresh air is being pulled in, fuel is added to that air, the spark plugs ignite that compressed air, because notice the volume has decreased. The compressed hot air now expands doing work and then leaves through an exhaust port. You might notice there are no valves on this engine. If you're a fan of Mazda RX-7s, you know exactly what this is. This is a Wankel engine, or a rotary engine. And Mazda was one of the few manufacturers that built this and actually put it in a production car. And a lot of people love these engines because these are, talk about a lot of horsepower per cubic inch and very high mean effective pressure engines. Here you go, this is it. The problem with it is that the part that's not shown is the rotor, and the rotor is sort of almost a triangular shape. And the problem with the rotor is that instead of being a piston, which has a large cross-sectional area for very small perimeter, so it's easy to seal as it moves, in this case the rotor had 3 lips that had to be sealed, and that wasn't so bad. That wasn't much line length. But then the side faces of this very large object had to be sealed, and you run into friction problems there. It's difficult to seal. And so that really is the Achilles heel of these engines. And while these can produce a whole lot of horsepower for a very lightweight engine, so you get a really nice fast car. You could damage these engines fairly easily. They were notorious for needing rebuilds after a small number of miles, but they were fun while they lasted. So pick your poison, I guess. But anyway, the reason I show you this is because we're going to apply the Otto cycle to a piston cylinder device, but the Otto cycle would apply to this Wankel engine as well. One of the reasons the Wankel was so powerful is because you only see one side of that triangle, or roughly triangular shape. There were actually three at the same time, so there were one rotor was acting like three pistons essentially. So in a very small engine, you could get essentially the performance of a 6-cylinder engine, which was pretty good. And then if you soup it up, I mean, you could really squeal the tires with this thing. So while we can't even differentiate with this idealized Otto cycle between a rotary engine and a piston engine, which probably seems like pretty rough resolution, while we can't differentiate between the two, we'll still be able to say something interesting and useful about both. So basically what we're doing here is developing an idealized thermodynamic cycle for a spark ignition cycle. Now we're going to develop it by considering what happens in a real engine and seeing how we can approximate each of these processes. There's not exactly a one-to-one correlation between all of the processes in the real cycle, but it's pretty close. So let's go through it. Now in the real engine, what happens is a charge of air and fuel typically comes into the cylinder. The piston is near bottom dead center, and it moves up, compressing the air-fuel mixture. Now in this process, ideally you'd like for it to be reversible, right? You'd like for it to be not fast compression so that you compress reversibly. You'd like there to be no friction as the piston moves up against the sidewalls. Of course there is some, but trying to minimize that with oil or something, they do a good job of designing engines these days. So it's not a bad approximation to say that this process of compressing the air-fuel charge is a reversible isentropic compression. Now I jumped from reversible and was talking about friction to isentropic, and that's a whole different thing, isn't it? I mean, yeah, reversible is a piece of that, but the other piece is adiabatic, and you probably know as well as I do that if you don't have coolant in your engine's going to melt, right? It's not a good idea to run an engine without coolant. So certainly during the compression process there is cooling that occurs of these gases, this air that's being compressed. But think about it for a minute. Do a back of the envelope calculation. Low RPMs in your car is 1,000 RPMs. That's essentially idle. If you're going down the highway and turning 3,000 RPMs, how quickly is the piston moving up and down and taking in fresh charges of air? Do the math if you want. It takes 2 strokes of the piston, so 3,000 RPM is basically 1,500 strokes per minute. Figure out how long that air has to contact the sidewalls and actually cool down. It's not very long. So neglecting any heat loss from an individual charge of air and fuel is not that bad of an approximation. And of course we always try to make it as reversible as possible. So reversibility plus adiabatic equals essentially isentropic. So that would be the best that we could do, is isentropic compression. So our very first idealized process replaces the compression stroke, which you see there on the real cycle, with the idealized compression. So from state 1 to state 2 in the lower PV diagram, we've got our first idealized process of the cycle. It's the isentropic compression of, in our case, remember we've assumed away the fuel, it's just air. So to show that there's no heat transfer, we've covered the whole cylinder in some insulation. The next process that occurs in the real engine is the compressed gases are lit up, right? It's got fuel, the spark plug goes off, that starts the burn, and really what happens is that burn takes some time. You don't want all of the air and fuel to ignite at the same time. If that happens, it's almost like a sledgehammer hitting the top of the piston. It's an impact type force instead of a smooth power stroke where the fuel has a little bit of time to burn. It's not good for a real engine. So in reality, the piston actually moves a little bit. It's moving up, the spark ignites, it starts moving down as the flame spreads and burns, but it's not that much. And there is what you would call a pressure spike, where the pressure does rise fairly rapidly from the point of ignition to the end of combustion. And even though the piston actually moves during that time, it's moving near the top of the cylinder. And if you know anything about the mechanics of the kinematics of the connecting rod and piston and the crankshaft, you know that there's a lot of acceleration near the top, but there's very low velocities. And so this approximation we're going to use of just allowing the piston to set at top dead center while heat is added to the air for, to represent the burning process of the gasoline, it's not that bad of an approximation. So from state 2 to state 3, we just let the piston sit at top dead center, so you notice that the volume at state 2 and state 3 is equal to each other because the piston is just sitting there, and heat is transferred into the air in order to get a working fluid that's capable of doing some useful work. So, at this point in the real PV diagram, in the real process, we're at the end of combustion. For the idealized cycle, we're at state 3 at the top left of the lower diagram. Continuing along, in reality, in the real system, what happens is some expansion occurs during the burning process. And after that expansion occurs, the cylinder or the piston is pushed back up the cylinder to exhaust the gases, the waste gases out, and then the piston moves back down to bring in a fresh charge of air-fuel mixture. So here's where we're kind of going to break with that, because we want to break it up into an expansion stroke, and then you'll see what we do with the exhaust and intake here in just a second. So in the idealized process, instead of considering the expansion stroke as part of the combustion, what we'll do is just say, okay, heat's in the air, that's done, and from state 3 to state 4, we're just going to have another isentropic work interaction process where the air is allowed to expand. So the air is going to push the piston down doing work. Notice in the first process from state 1 to state 2, we had to put work into the cycle, but the air was cooler then. Now from state 3 to state 4 during expansion, the air is a lot hotter, it has a lot more thermal energy, and so it will do more work output pushing the piston from state 3 to state 4 than the work we had to put in from state 1 to state 2. And we're not making energy from nothing here, right? Heat was added to that air, and really what we're doing effectively is converting some of that heat into work. And so from state 3 to state 4, we've got our isentropic expansion process, just like state 1 to state 2. This would ideally be something where no heat transfer occurs, right? So there's no significant change in the amount of energy the air has, except, of course, for the energy that's coming out due to pushing the piston down. So the only energy the air loses would be energy that it loses not via heat, but via doing work. And of course, ideally we'd like this to be frictionless, reversible, all those good things. So we've kind of broken with the real system, where in the real system we were at the point where the exhaust valve opens, but our next figure continued through the exhaust stroke. Now look at the real diagram for just a moment and look at the idealized diagram. The idealized diagram is pretty easy to see. This is a PV diagram, so the area enclosed by the cycle represents the net amount of work. Fine. But the real cycle looks a little bit confusing because we got kind of two regions that are separated off, right? The upper region represents work that's done by the engine, the net work we get out, but there's an amount of work on the lower region as well. Now if you're really sharp, you might notice that essentially the upper region represents a clockwise rotation, whereas the lower region is represented by a counterclockwise rotation. Now that's not exactly true, because after the exhaust valve opens, if you trace that curve, you don't just go back into compression. You go down into the exhaust stroke and back to the intake. But the point still remains that notice that the upper area is a lot bigger than the lower area, and what this really means is that the net work produced by the engine is a lot larger than the amount of work required to push the exhaust gases out and pull in a new fresh charge of air-fuel mixture. So in our idealized system, we're going to completely neglect the exhaust and intake stroke, because the whole point of those strokes is to get a fresh charge of air. Basically, it's to cool the air back down. Right, that's the point. And since not much area is enclosed by that exhaust and intake stroke, we can safely neglect it. So finally, in the real cycle, we come back, have our intake stroke, and we're ready for the intake valve to close and go back to the beginning, right? Complete the cycle and drive our car down the road. In our idealized cycle, what we're going to do, remember we're at state 4 at the end of the expansion work producing process. We're at state 4. And we're just going to let the piston sit at bottom dead center and let the heat of the air, or I shouldn't say it that way, let heat flow out of the air, reducing the thermal energy and therefore the temperature of the air, before we go back to compress it from state 1 to state 2. So notice that we're really capturing the whole point. And if you think about it, it makes sense, right? Because after the exhaust valve opens and the piston in the real device goes up pushing the exhaust gases out, where does it end up? It ends up back at bottom dead center by pulling in more air and fuel. So we could just let the piston sit there in our idealized cycle, since not much work is associated with moving that piston up and down, and just imagine the air cooling down and its thermal energy being lost to wherever. So this is our heat rejection process. So our idealized spark ignition or Otto cycle is as shown here on the PV diagram. Now, one thing you need to do as we go through these cycles, you need to have your book open to chapter 7, because all of these cycles are very important. In fact, what you'll find is that referring back to the cycle diagrams is very, very useful, especially in exams. So what I want you to do is get some tabs and make sure you bookmark all the pages where we find all of these cycle diagrams as we go through. So here's the first one. I don't remember the page number. Go to your book, find it, put a tab there and label it Otto cycle, because the PV diagram for the Otto cycle is important. However, there's also another diagram for the Otto cycle that's very important. It's the TS diagram, the temperature versus entropy diagram. So you need to find that one in your book as well. And notice we're just trying to note where the idealized cycles are located. So the idealized PV diagram for the Otto cycle and the idealized TS diagram for the Otto cycle are two very important diagrams. You might even want to highlight the figure number or something so you can find them. But you will refer to them quite a lot when you're working a spark ignition type problem. So now let's consider the math behind this. We set this up very carefully so that each of these processes are processes that we could analyze with the tools we have so far. So from state 1 to state 2 is an isentropic compression process. We were doing that basically all the way back in closed systems. 2 to 3 is a constant volume heat addition process. 3 to 4 is an isentropic expansion. And 4 to 1 is a constant volume heat rejection process, stepping around the PV diagram. One thing that confuses students, be really careful about this. Students see this PV and TS diagram together and they think, oh, well, the lower right state is the lower right state in the other one, and the lower left state is the lower left state in the other one. That's not the case. Be really careful here. Notice the state numbers are numbered consistently, and by convention, state 1 is at the beginning of the isentropic compression process. State 1 on the PV diagram is the lower right-hand corner. On the TS diagram, it's the lower left corner. So be really careful about that and don't confuse yourself. Now notice that from state 1 to state 2 on the PV diagram, it's labeled as an isentropic or constant entropy process. It's actually really easy to see that on the TS diagram, because state 1 and state 2 are on a vertical line and therefore have the exact same entropy. Just like it's easy to see on the PV diagram that state 2 to state 3 is a constant volume process, as is state 4 to state 1. It's not as easy to see that on the TS diagram. Of course, it's labeled, right? V equals constant from state 2 to state 3, and V equals constant from state 4 to state 1. Just as the isentropic behavior is labeled on the PV diagram from 1 to 2 and 3 to 4. But until you get used to seeing these and recognizing them, you'll want to refer back to these diagrams quite frequently, so make sure you mark them. Since we're dealing with a piston cylinder device and it's closed all the time, we can simply use a closed system energy balance. And here it is, and I've adopted the nomenclature of Q in and Q out rather than having just, Q in is positive and W out is positive. Instead, I put them in their proper order so we can talk about the net amount of heat transfer and the net amount of work. Now, not all these processes have work interactions or heat interactions, but this is our generic energy balance that can talk about what's going on in any of the processes. But it turns out that this equation usually is only useful for particular processes. So you typically won't have to derive what I'm doing right now, but you do need to understand it. So the energy balance will be particularly useful on two of the processes. The process from 2 to 3 and from 4 to 1. So if we apply the energy balance to the process from 2 to 3, what's happening is heat is coming into the process. In the real cycle, what's happening is the fuel is being burned in the air. Now, in our idealized state, the piston's just sitting still, and all that happens, there's no work interaction because there's no volume change, right? No area under the curve from 2 to 3. What happens is thermal energy is added to the air via heat. So basically what happens is the temperature of the air changes. And so there's no heat flowing out, so that term goes away in the energy balance. There's no work interactions, those two terms go away. So essentially we have a delta U, a difference in internal energy of the air from state 2 to state 3. Now state 3 is the final state, and so we write U3 less U2 and approximate then as CV delta T. Now remember, CV is associated with changes in internal energy. That's why we're using it instead of CP. There's no work interaction to include here. So it's just CV delta T to represent the internal energy change of the air as the fuel is burned. 4-to-1 also is a process where the energy balance is particularly useful. Notice that this process occurs on the PV diagram, but I've just pointed to it on the TS diagram, and I want you to note that both Q in and Q out occur, basically 2-to-3 and 4-to-1 occur, in both the PV and the TS diagrams. It's just easier to point to it and point out that they occur in both diagrams. So Q out occurs in 4-to-1. Remember, that's in our real engine, the process where you open the exhaust valve, push the piston up, close the exhaust valve, open the intake valve, pull the piston back down with a fresh, to get a fresh charge of air and fuel. And so that's our, idealized, or our real process that we're idealizing here in 4-to-1, where we're just taking the air, piston at bottom dead center, and transferring heat out of the air so that its temperature goes down. 4 is, of course, the final state. 1 is the initial state. And so Q out is simply equal to delta U, or CV delta T, between those two states. Now that's all well and good. We've used energy balances. We could apply energy balances to the other two processes as well, but it turns out it's more useful to apply an isentropic equation. Remember the first, second, and third isentropic relations? We have our choice, right? We can choose whichever ones we want. Since we've already dealt with temperature, and by the way, temperature is pretty much the king. It's the thing you need to deal with all the time in thermodynamics. So anytime you're trying to solve a thermo problem, temperature is almost always the go-to variable. It's one of the most important because it really represents, how much thermal energy there is in a substance. So we're going to use the isentropic equation that involves temperature. Well, that's the first and second. But then we'll use the one that involves volume rather than pressure. And the reason for doing that is because, these are PV diagrams where we know something about the volume. We really don't know much about pressure. Yeah, okay, pressure is on the vertical axis, but the volume is closely related to something we typically know or can design in the engine, and that's the compression ratio. So notice that we've got a volume ratio, and most often that volume ratio can be represented by a compression ratio. In fact, this particular volume ratio, V2 over V1, is the compression ratio, or it's 1 over the compression ratio, right? Because it's the volume at top dead center over the volume at bottom dead center. So that's exactly 1 over R. If we apply an isentropic equation to the process from state 3 to state 4, the power stroke essentially in the real engine, then we get a relationship between the temperatures in the two states, state 3 and state 4. And again, we have two volumes, V3 and V4, that could be represented as a compression ratio because V3 is less than V4. And so again, this is the inverse of the compression ratio, if I'm thinking right. Yeah, that'd be right. So this is the inverse of the compression ratio again. Now, copying all of this stuff to to another slide and getting rid of our PV and TS diagrams, we can do some math here. What we're really interested in is thermal efficiency. Thermal efficiency can be written as 1 minus Q out over Q in. Notice we have two equations, one each for Q out and Q in. So we can plug those into the equation for the thermal efficiency. And here's what we end up with. Notice that the two heat capacities cancel each other, so that's gone. That's kind of nice. But the temperatures, of course, don't. Now, you can't just plug in this fraction exactly as it is. Obviously, that doesn't work, right? Remember your math, it doesn't work that way. But T1 and T2 do appear in the equation, so do T3 and T4. I'm not going to show you all the math, but with a lot of math effort and algebra, you can get these temperature ratios into the thermal efficiency equation, and it actually ends up simplifying almost by magic to this. It's not magic, obviously, it's just math to get you here. But you end up with a really simple form of the thermal efficiency for the Otto cycle. It's 1 minus, no surprise there, that came from the initial equation, 1 minus 1 over R, the compression ratio, to the power of K minus 1, where K is the ratio of the heat capacities. I think this is amazing that it comes out this simply, but this is where you end up. And so this is the thermal efficiency of our idealized cycle. Now notice it's a little different than the Carnot efficiency. The Carnot efficiency was 1 minus TL over TH. This isn't saying much about temperature. It's talking about R, which is a compression ratio. And this gives us an idea on how we could improve the efficiency of spark ignition engines. If this is the efficiency, well then we could plot the efficiency as a function of the compression ratio R. And that's what the first graph does. notice that the efficiency goes up as the compression ratio goes up. And typically, spark ignition engines have compression ratios in the range of 7 to about 10, although they are going a little higher than that these days, because if you don't squirt the fuel in from the very beginning, it doesn't begin burning. And so if you have a fuel injector right into the cylinder, which is direct injection, well, then you can compress the air a lot more before you start squirting the engine in, and it can be very advantageous. So anyway, the higher the compression ratio, the higher the efficiency we would get out of the engine. And this is a good idea on how we could improve the efficiency of the typical spark ignition engine. Of course, the problem is detonation. If you have air mixed with fuel and you compress the air too much, the fuel will get to such a high temperature that it'll just start burning spontaneously. You've seen that in the fire tube that I had, where we put a little bit of napkin or something in the bottom of it, compress the air very quickly by smashing the plunger. The air gets up to such a high temperature that it just begins burning and reacting with the fuel, and that's what can happen here. Now you might say, well, I buy high octane fuel because it's got more energy and it's a better fuel. Actually, high octane fuel is more difficult to burn. The reason that it prevents detonation is because it's harder to burn. It's more of a closed form of molecule, and it's harder for oxygen to get to it. Basically, the oxygen has to burn away some of the fuel before it can attack the core and burn the remainder of the fuel. If you look at the octane rating on diesel, for example, it's a lot higher than even high-grade gasoline. Doesn't mean you ought to mix gasoline with your gasoline with diesel and put it in your car. That's not a good idea. It has to be formulated right. But yeah, higher octane gas is actually gasoline that's a little more difficult to burn. It'll still burn fine, obviously, if you started a campfire with it or something, which is a really bad idea. Gasoline burns a lot more efficiently if you control its burn, but if you burn it in open air, it produces horrible black smoke. You don't want to be around it. That's a bad idea. Notice there's another variable in here that could be changed, and that is the ratio of heat capacities. Now, the ratio of heat capacities is really the ratio of heat capacities for the working fluid. It's not practical to have a working fluid that is, say, helium in your car. That's just not practical, right? The helium's too expensive. Air is all around us. It's got an oxidizer built into it called oxygen. Why not just use that? And so there's not much option of changing the ratio of heat capacities in order to increase the efficiency of the engine. But if you could, change the ratio of heat capacity, you could change the efficiency. So here's a plot of the thermal efficiency versus compression ratio, but including the effect of the thermal conductivity ratio of the working fluid.